Hello, this is Tamo Miyake, a postdoc researcher at Waseda University, Tokyo, Japan. Our presentation is about development and evaluation of treadmill-based video see-through and optical see-through mixed reality system for obstacle negotiation training. One of the serious problems of aging is falling during walking. It makes us decrease the activity frequency, then finally bed rhythm. Because tripping is the main cause of falling, decrease of risk of tripping is necessary. As shown in figure, people change their toe height adapting to the environment. Usually the toe height is low to reduce energy. But if we recognize the obstacle, we lift the toe using energy. Tripping occurs in case of failing to control toe. Improvement led to visually guided and anticipatory adjustment of locomotion for upcoming obstacles is important. Vision plays an important role in obstacle negotiation. This is because vision provides the spatial temporal information regarding a remote place very precisely, and understanding the anticipatory nature of the adaptive locomotion is therefore particularly helpful to understand how vision is used to adaptively control our locomotion. Foot movement patterns are adjusted at least a few steps before obstacle. Foot placement is decided based on a specific rule involving minimum displacement from the normal landing point and a relatively consistent toe clearance from the obstacles. Gait training has been focused on for improving the locomotive control ability. People could adapt to unbalanced state caused by a perturbation system such as tripping-induced system or learn the gait motion guided by an assistive robot. For tripping prevention gait training, existence of obstacles eliciting visually guided and anticipatory locomotive control is important. However, training environment is limited. A small space, a few variety of gait conditions, a few variety of environment conditions. In terms of obstacle negotiation, use of real obstacle has a limitation, change of obstacle types, and place where the obstacle was located. Recently, mixed reality or augmented reality techniques have been used to augment environment. These techniques give us interaction with both physical and virtual objects at the same time, in the same frame of reference, using natural input from the user. Previous researches show the potential that MR mixed reality obstacle can elicit real obstacle negotiation. However, the investigation was conducted only for level ground walking. The feasibility of using virtual obstacle on a treadmill, where gait training is often conducted, remains uninvestigated. Accordingly, we take the first steps to explore using treadmill-based MR techniques in obstacle negotiation and to investigate their effect on users' obstacle negotiation performance. Combining MR with a treadmill allows training to be conducted in a smaller physical space and without a variety of obstacles for the training. Accordingly, we focus on evaluation the feasibility of using an MR obstacle negotiation system deployed on a human-centered treadmill system that allows people to walk at their own pace. We assume that whether the obstacle negotiation performance elicited by the mixed reality treadmill system could be changed from the real one, depending on the visualization methods. We focus on two types of mixed reality head-mount displays that have high visual fidelity and can easily be accessible and deployable in various training contexts, where each has a different mixed reality visualization method, video see-through and optical see-through. Video see-through mixed reality system was deployed to project a moving obstacle on treadmill using HTC Vive. An optical see-through mixed reality system was deployed to project a moving obstacle on treadmill using HoloLens 2.
Go. Go.
Two types of obstacle with matching shapes and dimensions were prepared. The height of the obstacle was determined by considering that the previous study used the box with a height of approximately 10% of the leg height of the participants. The box is an obstacle that has height, width, and depth, and is put on the ground. The rope is an obstacle over a thin line in the air. Each participant was familiarized with the system before starting trials. First of all, they walked on the treadmill for 5 minutes without any head-mounted displays and any obstacles. The familiarization practice was also conducted for obstacle negotiation with all prepared obstacles, where they practiced stepping over the obstacles while using the treadmill. They walked at their self-paced speed once they had started steady locomotion. There were 6 trials for each condition. Spatio-temporal information of foot movement when obstacle was approaching the participant was analyzed because this information was the output of obstacle negotiation. First video shows the condition of real obstacle without any head-mounted display. Second video shows the mixed reality obstacle with HTC Vive. And third video shows the mixed reality obstacle with HoloLens 2. Figures show the foot height for Vive mixed reality, HoloLens 2 mixed reality, and without any head-mounted display. Real obstacles. 12 people joined the experiment. Leading foot height for Vive mixed reality condition was significantly higher than the real condition in case of box. Leading foot height for HoloLens mixed reality condition was not significantly higher than the real one for any obstacles. Actually, the timing adjustment for stepping over obstacle was delayed in the Vive mixed reality condition compared to the other real and HoloLens 2 mixed reality conditions. The tendency of delaying the adjustment of steps at 2 steps before stepping over was observed for all obstacle types, but only the box condition caused a significant difference for foot height. We also compared the foot height when stepping over the same real box obstacle when using 3 types of head-mounted display conditions. Figures show the height of the leading foot and trailing foot corresponding to each head-mounted display condition for real obstacle. The height of the leading foot between the real obstacle without any head-mounted display and Vive real obstacle, and between HoloLens 2 real obstacle and Vive real obstacle was significantly different, even though the obstacle is exactly the same. The height of the trailing foot between the real obstacle with head-mounted display and Vive real obstacle was significantly different. Consequently, visualization condition affected the foot height control. This is the conclusion slide. In this study, we presented a novel mixed reality treadmill system for obstacle negotiation training. Our system comprises 2 main components, a treadmill system and a mixed reality system that integrates both video see-through and optical see-through head-mounted displays and obstacles. The video see-through system has shown that it has a significant effect on the user's obstacle negotiation performance in the case of box obstacle, which we believe was mainly due to the challenges of the latency displayed in the environment. Further comprehensive investigation considering the effect of different latency of the camera view, calibration, interpolating distance, convergence, accommodation, and other factors of depth cues would be conducted. It is important to extend our study with other virtual obstacle types, varied and larger user sample sizes, and other head-mounted displays implementations. In addition, the gender effect and age effect should be explored in future work. Thank you for listening to our presentation.